we live? Hello, 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 hello. Welcome. So good evening. Back here again with another question to work on. Let's see, is the volume? Yeah, I think the volume is a good spot. I don't want to, I'm probably going to keep my voice a little bit lower, but I don't want to, I'm probably going to keep my voice a little bit lower, but I don't want to like amplify it too much, because I tend to have the volume a little bit too high, I guess. So here, back with another question to work on. Let's see how we do. So lexicographical numbers is what we're going to look into. Take a look now. All right. So given an integer n, return all the numbers in the range 1 to n sorted in lexicographical order. Check that out. No kidding. Constraints. N is 5 times 10 to the 4th. Well, I mean, you know, you could do this with, there's a few things you can do. I mean, you can do something like this. Can you do this? Let me try this. Iota. And just want to see something. I just want to see what this looks like. Yeah, it's kind of what I'm expecting. So from 1 to n. So 1 to 13. Okay, yeah, that's what I was hoping for. All right. So that works as expected. And then what we want to do is probably transform. Use this quick Lambda function, which basically takes int x and returns standard toString of x, and actually I should do the same thing. Writing this again. See what that looks like. Oh, we also want algorithms. Oh. Really? I don't use that too often. I don't really know the syntax too well. Oh. No kidding. Can we do into the same vector. No. Oh. Oh, yeah, that makes sense. That makes sense. It's my mistake. Zero offset to null pointer. Huh. What? Excuse me. Oh. Interesting. Huh. Excuse me, I wanted to change the name. I want to change the name of this. And we can do... What? That wasn't what I wanted. No. No kidding. Anyway. Really don't need a Lambda function here, do you? Gotcha. That's fine. Function that calls the toString function is not a big deal. Actually, let's try that. I don't know. Whatever. It doesn't matter. Probably could use toString somehow, but we're not going to do that for now. Surprisingly, this is taking a little bit longer than I thought it would. This, by the way, this is the brute force approach. Yeah, I guess like the not brute force approach. I don't even know what you call it. I'll tell you. I'll describe in a second what this is. So basically, this, in simple terms, you're kidding, really? Oh, really? Oh, okay. Wow. Never mind. Whoops. That doesn't even matter then. Take it back. This actually is easier than we thought. Hold on. It's taking me a while to code it, but this is pretty straightforward. Believe it or not. I think it's just simple. Yeah. I think it is that simple. Let's go for it. See how we do. There we go. Alright. Oh! How did we do? 11 minutes? Okay. Not amazing, but okay. Yeah, so the deal with that is a few things to note. Basically, a few things. So, yeah, there's a few things to say. So the first thing is we have to actually return a vector of all these items. So that allows us to do a lot. That allows us to create the vector of that size. That allows us to fill a vector of that size. Right, this is all linear with respect to the size of this thing. Right, so you sort of have a lower bound on like operations you can do, which is linear. So, and then finally we can sort that. And this is technically constant time to convert it to a string. Now, in truth, it's like really expensive to convert all these numbers to strings and compare them. However, it's doable. It's only a constant kind of multiplier. So that's why it took 800 milliseconds, whatever it was, a huge number of milliseconds, because this is the comparisons that are being done are basically converting the numbers into strings and then comparing them and then moving the integers where they should be based off the comparisons. And then the sorting routine is n log n, which is not much more expensive than linear time, so it's not too bad. Now what they're suggesting here is, can you do this to linear time and not use extra space? And the reality is you can't really do too much about the extra space, because you do need a vector to return. Like, they want a vector of these numbers. Linear time you probably could do using counting sort instead of the regular sort, which I guess you probably you would probably need to implement the counting sort. And in fact, since these are unique numbers, counting sort is, I guess, sort of easy to do because of the these are, I want to say, like, the sorting algorithm that you can use is easier because these numbers are it's sort of every number is unique, and it's exactly the consecutive numbers. So I think it wouldn't be that hard to do the counting sort. Like, I don't think you can do better than this part right here. Like, you kind of need to fill an array full of these numbers. I don't think you really have an option. How you sort it, though, is you definitely have some leverage there. So that was why I was pretty confident that this would work, because obviously none of this code is really like, none of it's sort of custom. It's all kind of like built in from the STL, and it's also like, there aren't very many lines here, and there's like not too many options for what you can do, sort of based off like the problem statement. So I was like fairly confident that this would work. It was pretty close though. Like, we were actually pretty slow. Now we could, two things that will speed things up. One is we don't need to convert to strings this way. Like you could do something different, which would be something like the following. Which I think would be faster. which is kind of what I was doing before. Would be a little bit faster, not too much faster, but you could do this too. Something like this. And then you can sort, without this comparator, these two, temp, temp. And then what you can do, actually what we want to do, copy that and then back up. And then we can actually transform again, transform back. Oops. Call that X or T, I don't know. M, N, call it N. I'm not sure what to call these things with these different. We're going to do temp begin. And then result begin. And we're going to do back the other way, which is from a string. It's going to be iota, it's going to be I to S of X. Something like this. What does that say? N. Redefinition of N. Oh. LMNOP. We'll just call it M2, I don't know. Or alpha. So we're using Greek letters. Compiler. No I to S, really. Iota, or I to A, I to S. Oh, it's the other way around. It's S to I. My mistake. I forgot. Stoy. S to I. Okay. Oh, we don't use M anymore, by the way. Okay, let's try again. Man, what is going on here? Whoa! Applying non-offset to null pointer. What is that error? What is going on? M transform temp begin. Want to sort temp end. Okay. What? Oh, that's why. That's kind of a subtle thing. Yeah, okay. Yeah, that works too. Alright, let's try running that. That's a lot faster. Yeah, that's a lot faster. That's what I was saying. We're thinking. The reason why this is a lot faster is because we only do the conversion once, to the two-string conversion once for each number, and then we sort, and then we convert it back one time. because they want integers rather than the numbers themselves. So this is a lot more efficient, as you can see. This is about almost 10 times more efficient. Let me see if I can run it a few times what happens. I was almost afraid this would be slower, but yeah, like I said, doing these conversions and comparisons on the fly is extremely inefficient. Now we can write our own counting sort to do this sort more efficiently as well. However, I think we probably could write. Let me see something here. Like the lexicographical sort, we could probably write a lexicographical sorting routine on a number by number basis, and I guess it would be, yeah, it could be like a Radix sort, basically. We could write a Radix sort and do that instead. So that's two different ways to do this already, and then we'll do one more. Well, let's do it. We're going to write our own Radix routine. Actually, let me see. Yeah, we'll write a Radix routine. That's fine. So here we go. It's going to look like the following. All of this goes. You do a simple sort, result begin, result end, and you use Radix. And you actually don't even need to do that. Well, okay, we'll do that. Fine. Whatever, we'll do that. This I think would also be. It's not a Radix sort, but you could use Radix kind of logic to. This I think still won't be as fast as it could be. We could use a counting sort that has special logic, our own custom counting sort that has special logic. I think that would be the fastest way to do it. And so what we say is, we go digit by digit, and we say, compare the most significant digits first. I think the problem here is that you need to actually get that's really tricky. I actually don't know how much more efficient this will be. I want to say something like you can do just first do a comparison on the length, and then you've got to actually get to do a comparison digit by digit. Actually, if they're the same length, then it's just an integer comparison, really, at that point. Is it? No, it's not. Yeah, actually, I think it is. Yeah, I think actually it is. So let me try this again. Although there's an issue of if they're not the same length. No, I don't know. The problem is that you've got to compare the most significant digits first. Yeah, what's interesting is that even though this is not, no. No, I don't think this is going to be very efficient. I think it's actually more efficient to just convert them to strings and compare them than what I'm about to do here. Because this 2 comes after all the things with the 1 in front. Less digits comes before the ones with more digits. But not always, not in all cases. Oh no. The problem with doing a digit by digit check is you kind of need to get all the digits, because you compare the most significant digits first. I guess you could. Alright, let's try this. We'll do L1 is standard log base 10 of A, and L2 is int log base 10 of B. And the problem with this is you have, excuse me, if A is 100, log base 10 will give you 2. So it's plus 1, right? If you have, yeah, I think it's plus 1. We'll just say plus 1. Sort of this would be like the floor. When you truncate to an integer, it sort of takes the floor function. Now what you can say is int position 1. Yeah, position is going to be standard. Do position 1 equals power of 10 raised to L1. Position 2. Yeah, see, this is actually really expensive to call all these routines just to compare these two values, numbers lexicographically. This is like a lot of extra machinery, a lot of extra stuff. Okay, here's the deal. If you have, yeah, we'll do L1 minus 1 and L2 minus 1. Right, so if this is like 900, you'll get 3 digits for L1. And you really don't need this plus 1, do we? We really don't need that, do we? No, I don't think we do. Well, I guess it's fine. So now what we do is we say, we can get that digit. We say if, well, really it's a while loop. And we'll just say L1 and L2. And decrement both of these as we go. And we don't really need this, do we? This extra 1. I don't know if that really matters. I'm gonna remove it for now. Come back if we need it. I feel like I probably should have just finished as we were, but yeah, we'll do that. And then we say, okay, digit 1 is going to be A modulo, right? So when you divide, not modulo, divide by position 1, and D2 is B divided by position 2. And we say, okay, compare these two. We say if D1 equals D2, then we'll continue, right? If they're not equal, or if D1 is less than D2, return A, or yeah, return A less than B, which is true, right? A is less than B. D1 is greater than D2. return false. Otherwise we keep going, and then we get all the way through. If now I want the smaller of these two. The smaller of the two is the one that's 0. So we say if d1 equals 0, then return true. Else if 2 is 0, return false. And finally, otherwise, you're going to return. Now, if they're both equal to each other, then it doesn't matter what you return. Right? That means that all the digits are the same. It's the same number that you're comparing. Okay, something like this. And also, you need to update the positions themselves afterwards. Bit should shift over by 10. Both cases. Now this is something here. Log, really. Somewhere around here is a log. Okay. CMath and log 10 is what we want. Log 10, yeah. So we'll get CMath and we'll do log 10. Probably only need one parameter at that point. Let's see how that goes. Oh. Yeah. Let me try that. Initializer notation there. I like that. Alright, output 1, 3. Why is it back? Why is it backwards? What is going on? Hello? Huh? What happened? What? Nice. That's what I like to see. Okay. Very interesting. And then, wow. Huh. Well. Right. Of course. Of course. Excuse me. Log base 10 of 13 is not 2, is it? No. That's fine. Oh. Gotcha. Compare that equal to 0, huh? Yeah, we can just do this. Whatever, it's fine. So if we're looking at 1, well, what happens if we do this now? That's a lot better. 10, 11, 12, 13 is what we wanted, but then 1 comes after 110. Now that is a tricky thing, right? Because not D1, it's L1. L1. That's why. In that case, we don't really need these. Whoa! No, still wrong. Fast, but for some reason, yeah, fast, but still wrong. What we're looking for is what we are looking for is L1 hits 0 before L2 hits 0. That means actually the other way around. The smaller of the two is actually larger. Confusing, but that's one part we missed. Okay, let's go with some other examples. Let's see how that goes. Wrong. No, really? Oh, no. Ah, come on, man. 1, 10, 100, 1,000, 101. Why? Oh boy. What happened? When you compare 1,000 to 1, you get basically you want A less than B is return true, and then not A less than B is false. That should actually be false, I think. That might be part of it. Didn't matter. One should be in front of everything. What happened to 1? This should never happen. This down here. So confused. Oh no, sure, this does happen a lot. I'm sorry. Well, this doesn't get reached because L1 or L2, one of these two has to be. Oh no, excuse me. Oh, I'm sorry. That's my mistake. That's why. And then so confusing. I think it's false if you do it this way. There we go. All right. That is. I realize it's very confusing. What's going on here, but it is what it is. All right, let's go for it. Hey, okay. That was quite the routine to compare two integers lexicographically. That's like a lot of work, a lot of extra work to just do instead of converting them to strings and comparing them. Still faster than converting them to strings and comparing them. However, kind of inefficient. Not really best. Still two things. One, this is still actually a n log n routine, and then here the comparisons between the integers directly is still pretty expensive because there are all these calls you have to make. So interesting, but not much better. Right, we were better off before just converting everything to strings, doing comparisons on the strings, sorting those based on strings, and then converting those all back to integers. Excuse me. What we can do now is what we can try to do is use a counting sort, a kind of a counting sort, and what we would do is there's a position. Every number has sort of a unique position. Now, what a normal counting sort does is effectively you could create an array of numbers, and then the numbers themselves would be indices to that array. And then what you would do is you would just basically put all of these numbers into the array, into their respective positions, and then read off the array again, if that makes any sense. Actually, it's not just that array. You put them into buckets, not just in the array. But in the array, it would be actually a list of these numbers, and then you would combine each of the buckets. But it's very much like basically dump everything into an array based off the numbers index, and then read off the array. And it's very simple. It's like a very simple algorithm for that reason. The thing that we're going to want to do here, though, is we want to use counting sort. However, the values themselves don't really have indices. That's the thing that's tricky about this. I don't know. Well, could, based off of n, generate all the sections of 1 through 9, something like that. Like you still could do a kind of radix generation type of thing. Basically, just generate all these numbers and add them to an array. You can kind of write kind of like an iterator that generates number after number. Yeah, something like that. Thinking. Something kind of recursive, I guess. Like a backtracking algorithm, something like that. Excuse me. So it goes 1, 10, 100, 1,000, right? Something like that. What does this look like? Yeah, 1, 10, 100, 1,000. Let's go all the way to the bottom. 10,000, 10,001. Yeah. Interesting. Let's write a backtracking routine. I like that. I think that'll be faster. Faster than all of this. Faster than all of it. Faster than all of it. Let's try that. So I looked at a few different ways to do this. I think the fastest way would be result n, or one of the more interesting approaches would be this DFS. And I don't know what we're going to put in the DFS here. Have a current integer, I guess, and we're going to say something like for int I equals 1, I is less than or equal to 9, plus I, you're going to DFS current F current F. And what we're going to do is we're going to change the state as we go. So as a base case, if current is greater than n, or we could say digits too. Max digits, we could do standard log 10 of n, so plus 1, right? Digits greater than max digits, and return. Current start off at 1. And the digits 1 digit. Say result dot push back 1 or push back current. And yeah, you would want to push this back first. So basically you push back. So you push back current and then you say, let's do 10 times current plus I. You don't have to add I. You do so what you would do is I want to say something like first push back current, and then you call f of 10 times current digits plus 1 f, right? You do that a few times, and then you say current plus I. Yeah, I could do 0 then. Zero and 0 digits, or 1 digit 0. Current plus I. Push back current. If current's not equal to 0, I don't know, this is a little weird what we're doing here. I don't know about this. I said it was going to be a backtracking question, but I seem to have got myself into an awkward spot. Excuse me. So current's not 0. Now we push it back current and then operate on 10 times current digits plus 1. And you do those first, right? So you do the larger digits first. And once you return from that, then you can do the add a digit. So first you're going to exhaust the digits, and then once you're at maximum digits, so like let's say we're at 1,000, then we're going to start adding and recursing on each of those, and each of those will time out, or not time out, but all 9 of those digits won't go anywhere here, and then we'll go back up 1 level. Have another digit added. Yeah, I think that makes sense. This call stack. And then eventually, I think that's all you need to do, actually. That might be it. I don't know. I don't know what happens here. Oh. And the digits. Oops. Same number of digits here. Oh, let me not run it on DLEs. Let's do this first. I'm actually not sure about this code. I have to run this a few times. This is a very unusual kind of a backtracking we're doing here. Oh, really? Looks very close, but we got to 12, 13, 13, 12, 13, 13. That's not supposed to happen. Yeah, I don't know about this. Let's do this. We have 9 digits that we add, we push. Before we do that though, we want to push this. Something like this. And the problem with this is it doesn't push anything onto the, doesn't do anything. I guess we would say if something like this maybe, I don't know. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we call this with a 1, current plus 1, multiply this by 10, call it on 10. But the problem is, no, this isn't correct, is it? No, it's not. Huh. I don't know. I don't know. I don't know. I flat out don't know how to write this routine. I don't know. I'm just gonna take it all back and say I don't know. I don't know. We have sort of like multiple directions almost where. Oh, damn, man, I'm tired. Excuse me, I'm not just tired though. I'm also unsure about this question. So I don't know. What do you do? Maybe so for 13 you would do 1 and then 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And then 2. Well, 13 you go 10, 11, 12, 13. And then 2. And then 3, 4, 5, 6, 7, 8, 9. So then the question is, how do you handle this? How do you deal with this? What do you do? I don't know. Gotta think about it, huh? We basically want to generate these numbers in the right order. Let's see. Start with a 1 and push that in, and then have a choice between either multiplying by 10 or adding 1. So you would defer to adding multiplying by 10. So you would recurse on after multiplying by 10. And I think what I'm doing wrong is you multiply by 10 and then you divide by 10 again, right? And then you would add 1 and subtract 1. Yeah, I guess that's fine. Right, so you have 3 options. You have one option. You have a few options, not a few options, but a few different paths to take. Multiply by 10, or add 1, or add 2, or add 3, etc. Right. And excuse me. And you always multiply by 10 first. And then if multiplying by 10 is not an option, then, which it no longer is at some point, really what you could do for multiplying by 10 is just have a digit. I think the code that I had before is pretty close. So you multiply, so you have 1, then you save that number, then you multiply by 10, you add the other digits. I think it was a little confusing because you would try to, well, you could do modulo 10 and say you could do like start initially at modulo 10 plus 1. Basically, there's a way to do this where even though you're starting off at 1 at the beginning, you could still have like the right routine. I think it was really close actually. Just thinking what could have gone wrong. Hold on, let me try again. Let me try this again. I actually think this is right, or it's really close to right. Maybe I'm mistaken somewhere. Excuse me. All right, let's try this again. So, base case, if current digits, if current is greater than n, or digits is greater than max digits. Turn. Excuse me. What we're going to do is result pushback current, and let's call f of 10 times current digits plus 1, f and 4. Now we're going to say int x equals, it's going to be current equal, divide equal, or mod equals, I don't know, divide equals 10. So you divide by 10, and then this is going to be, I don't know, temp is equal to current divide equals 10, or divide 10. X is going to be current modulo 10 plus 1. And then we're going to say x is less than or equal to 9 plus x. And we're going to call f of temp plus x. 10 times temp plus x. And it's a little confusing, but basically delete the rightmost digit is pretty much what we're going to do here. And then digits f. Okay. Yeah, that should work. I think that works. What does that do? So that should be a 1. Okay, that does not work. What is going on here? All right, we almost got this part. 1, 0, 1, 10, 11, 12, 13, 13. What is going on? Why is this happening? 10 times 1 will give you max digits. How many max digits? 1, 2. Okay. So we have 10. So we push back 1, push back 10. 100 doesn't work. So now we have 10. Right. And we call this 9 times. Right. And we get all these guys, or we call it, oh, see, 11, 12. When we call this a 3, it doesn't work, right? All the things past 9 don't work. And then all those, now I guess my question is, when you call this with 11, I think that's the problem. Yeah, I think I see the issue. You're not supposed to call all these recursive routines. I think I see the problem. I think I see the problem. Okay, I think I get it. I think I see the issue. No. This really is just I equals 1. I is less than or equal to 9. And what you're going to do is say current plus I, and you say if current modulo 10 equals 0, Then we can do these. Otherwise, you just print it. Yeah, basically. How about that? What happens when we do that? All right. Something like this. This is super awkward. This is really awkward. But it looks right so far. Let's not jinx it. Oh, look at that. Okay. It's convincing. How are we doing? How did we do? Oh, uh-oh. That looks like it might be correct. Uh-oh. Let's go for it. Hey, check me out. Hey, I'm the best. That's so funny. That's ridiculous. This is absurd. Come on, man. That's a lot faster. Yeah, that's a lot faster. Almost 100%. Oh, we're so close. Come on. Give me 100%. We're so close. Come on, one more time. 1, 2, 3, 4. How long are we on this? An hour? One more. Come on, 100%, 100%. One more time. 1, 2, 3, 4, 5, go. 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 All right, we'll give it one more shot, and that'll be the last one. All right, we got 97%. That's pretty good. I think you could probably do this iteratively too. Yeah, this is kind of funny, but I think it's maybe a little easier to understand if you do it recursively. But you definitely could do this iteratively as well. It's very funny. You could just make this whole thing a big while loop. It's great. This is great. Oh, also my stomach, my gut. I don't know if it's easier to do this with a while loop. This is like kind of confusing to make it into a single while loop. But I'm satisfied. 97% is pretty good. We probably could get 100% somehow. But I don't know. I feel like we would really need to push it for that. Anyway, yeah, that's a lot more efficient than these other ones, right? 868 compared to 4. So a lot of different ways to do this. Excuse me. Let me upvote this because I just like how many different ways to do it there are. And yeah, let me get going here. Thank you all for watching. I will talk to you soon. Have a good rest of your day. I thought this is a pretty interesting question. Challenging, definitely challenging. Didn't quite, I guess we're sort of not finished in the sense of like, probably you could also do this in an iterative way as well. However, that's something let's just say I'm not going to pursue that just yet. So yeah, thank you for watching again. I'll talk to you soon. Have a good rest of your day. I think I'll take a small break again and then probably pick up another problem shortly thereafter. So yeah, all right, take care.